Welcome to Beta Online Learning, and this is a video for the 10th Standard CBSE Mathematics on the topic All You Need to Know About Circles Part 2. While Part 1 of this video, we covered the basic concepts you learned already in 9th and 10th grades. In this video, we will see some advanced concepts about circles. Let us go to the concepts. What you need to know. In this video, we're going to cover what is a circumcircle, an incircle, an intersecting chords theorem, and in applications to problems, applications of these problems these concepts to these problems, we are going to see two hard challenge questions. We'll provide you the hints for the solutions for these problems after covering these concepts. First, let us see what is a circumcircle. A circumcircle, or a circumscribe as it is also called, a circumcircle is a circle that passes through all the vertices of any polygon such as triangles, rectangles, regular polygons, and some other shapes, but not all polygons. Triangles, basically, we are going to see here. The center of this circle is called the circumcenter. That is the center or the origin of the circle. And its radius is called the circumradius. That is the radius of the polygon circumcircle. In this figure, we see a circle circumscribing a triangle. And that circle is called the circumcircle. It has a circumcenter, the center inside a triangle. It is actually the center of the circle that circumscribes the triangle. And the radius, the line joining the circumcenter to one of these vertices of the triangle is called the circumradius. Let us see what these definitions are. Circumcenter is the center of the circumcircle. It is the point of intersection of the perpendicular bisectors of the sides of a triangle. We know that a point on the perpendicular bisector of a side of a triangle is equidistant from the two vertices. So that itself shows that there is it is the radius. And we can draw a circle. The distance of the circumcenter from a vertex of the triangle is the circumradius. If a circle is drawn with the circumcenter as the center and the radius equal to the circumradius, this circle will pass through all the three vertices. This is about circumcircle. Now, what is an incircle? An incircle, the circle that lies inside a triangle and touches all the sides of the triangle, is known as the incircle of a triangle. This figure you will see, this is the triangle, any triangle, and the point inside the triangle is the incenter. And the circle that is drawn with R as radius, which touches all the three sides, is called the incircle. In fact, this is the center is the meeting point or the point of intersection of the three angle bisectors of the triangle. Interior angle bisectors, as you will see, the interior angle bisectors OB, OA, OB, and OC, they all intersect at O, which is the incenter. And if you draw the circle, it will touch the three sides. In fact, the three sides of the triangle will be tangents to this circle. That is what it means. If all the three sides of a triangle touch the circle, then the sides of the triangle are tangents to the circle. Hence, the center of the circle is located at the point of intersection of the internal bisectors of the angles of a triangle. This point is called the incenter of the triangle and is equidistant from the sides of the triangle. Then only you can draw the circle touching the three sides of the triangle. Next, we move on to a very useful concept called the very useful theorem called the intersecting chords theorem of Euclid. When you have two chords intersecting within a circle, any two chords intersecting within a circle at a point P, let us say this, the two chords or the two lines that pass through that circle AD and BC. You can see the two chords AD and BC. Then the ratio of the segments AP by DP, the corresponding segments of the chord AP by DP is equal to BP by CP. Draw a circle that then mark all these points. You can see that this theorem can be easily proved using the concept of similar triangles. P is typically in the middle of the circle, but slightly off the center. It is not exactly at the center of the circle. It is also known as the power of a point within a circle. And this is the intersecting chords theorem of Euclid. We can also state this intersecting chords in a different way. So you can see this figure. The two chords, the intersecting chords theorem, also known as a chords theorem also, states that the products of the lengths of the line segments on each chord are equal when the two chords intersect within each other, within the circle. See, you can see that AP by the same thing. We say that the product, when we cross multiply these two terms, we will see that AP by AP into CP. You see this AP into CP, AP into CP, these two segments, multiplication, the product is equal to the product of the other two segments, BP into PD, DP, BP into DP. This can be proved by the similar triangles. Now we have joined the AB and CD here. We have marked these angles. The intersecting point is P, and we take the triangles APB and CPD, the same order, because we know that angle BAP is equal to angle DCP because they are angles in the same segment. One angle is equal. A pair of angles is equal here. Another pair of angles, we can say the vertically opposite angles here, APB and CPD are the vertically opposite angles. So by angle rule criteria of similarity, we say that triangle APB is similar to triangle CPD. Hence, the ratio of the sides by CPST, that is called the corresponding parts of similar triangles, we have BP by DP is equal to AP by CP. We can get it, the corresponding segments, the ratio of the corresponding sides are equal. The colored segments are being marked over here. AP and CP are the corresponding sides, which are proportional, and the other two sides, BP and DP. Okay. This is called the intersecting chords theorem. Based on these concepts we have learned so far, we have a few questions, two questions, but both are not fully solved. Only one has been fully solved here. The solution to this problem is based on the concepts you learned already in 9th standard itself. Angles in the same segment, angle sum property, and so on. So these are the This is a circle and this is the question itself. You can give this problem a try. It's rather simple, but it involves the concepts of circles as well as triangles, especially angles in the same segment, the angle sum property, and the exterior angle theorem. Exterior angle is equal to the sum of the interior opposite angles and so on. Some concepts we have to use in this in solving this problem. Let us go to the solution. This is the solution. To find angle CDE first part is to find angle CDE. So to find angle CDE, you can refer to the figure actually. See, angle CDE, CDE is actually, this is a cyclic quadrilateral. So the angle CDE will be 180 degrees. See, the opposite angles of a cyclic quadrilateral, what you learned in 9th, CDE plus angle CBE is equal to 180 degrees. They are supplementary, isn't it? So CBE, what is CBE then? CBE is 90 minus 180 minus 72, because CBE and ABE form a linear pair. This is, you add these two, this 72. ABE, CBE and ABE. AB is 72 degrees given. So naturally the CBE should be 180 minus this 72, and it is the same as CDE, which is the same as this, therefore it's 72 degrees, and we got the answer as 72 degrees. Isn't it? So that's simple. It looks hard, but simple. But the third, we'll jump to the third part. The third subpart is a little bit easier to solve than the first part, because the third part subdivision here is angle BCE, finding the angle BCE. Use the angles in the same segment. See here, angle sum property. Actually, when you go to this BCE, this triangle, this angle BCE is equal to angle BDE, the angles in the same segment. Here you can see that. But BDE is a part of the third angle of the triangle BABD. Look at that big triangle there. A, B, and D. These two, the big triangle, of which we know two angles. Angle ABD is 81 plus 72, which is equal to 153. And angle BAD is already given as 22 degrees. Add these two angles, you will get 153 plus 22, which is equivalent to 175. So angle BDE should be 180 degrees minus 175 degrees, and that is 5 degrees. So the third part, I have jumped to the third part because, and BDE, if it is found out, it is equal to BCE, angles in the same segment. So EDB or BDE, whatever it is, the same, is equal to angle BCE. So BCE is what we need. So if we find EDB is equal to 5 degrees, we got this by the angle sum property again, and then angles in the same segment. Now coming to the second part, it's interesting to note that the second part is very simple, as you can see from here. This part, we have to find angle CDB. CDB. When you want to find CDB, it is nothing but angle CDE, which we got in the first part. First subdivision, we got this angle CDE as the CDE already. We got the angle 72 degrees. got the answer, isn't it? So CDE minus angle BCE, isn't it? So that's what is going to be done there. Angle BDE is the same as BCE, which is 5 degrees already we found out in third subdivision. So what the answer we got in the first subdivision minus the answer we got in the third subdivision will give the answer in the of the second subdivision. Let us see that. See there. This is the thing. The second subdivision here. BDE is the same as BCE, which is angles in the same segment. Angle CDB is equal to angle CDE minus angle BCE. Should be BDE because BDE is already there. We have substituted for BDE, we have put BCE here, which is 5 degrees, already found in the third subdivision. First we do that, then only you can easily do this. Sometimes we have to do a little bit of jumping from one to the other to get the easy solution. Here we get a very easy solution. 72 minus 5 degrees, that is equal to 67 degrees. And that's the answer for the second subdivision. Seems to be hard, but it has been done in a very neat and smart way. As we move on to the next challenge question is intersecting chords theorem. Of course, this will be solved in a separate videos on a detailed solution. I will provide you a separate video on this. Since it's a concept here, we use the two methods we will use. These are two mutually perpendicular chords. First hint is given here. Method one is one method which we use elementary geometry and circle theorems, the Pythagoras theorem. Of course, it is quite easy to visualize this. We can find the, we can name this as M here, the point of intersection. See, that is what is given there. Point M, as shown in the figure, is given, but it is not marked here. We can mark it as M here. So we can find the missing segment, CM. The CM happens to be the CM, this part. This. So we use that AM into B, MB is equal to CM into MD. This this product, that one. And AM into MB. AM by MB should be AM into M. So AM, actually it is the intersecting chords theorem. It is, we use that concept and find out the value of M, that is the other chord. And we do some construction here. To find the center of the circle, this first part of the question, we have to find the radius of this circle. We don't know the center. We have to locate the center. If we draw the perpendicular bisectors of, two intersecting chords, we will get the center. The intersection of, point of intersection of the two perpendicular bisectors. I'll just show you. Just a minute. This part of the thing will come here as when we pass on to this one. This theorem is an important, this is a solution. Seems to be a little bit difficult, but when we use the second method, will be slightly easier. We will now come to the figure now. We'll present the figure now. Here is the figure. The first method is the algebra method, the method which is slightly more difficult. We'll form a quadratic equation like this and then solve it. For R, we will get an equation like this. We have to prove that, first of all, that segments, we will name them as W and so on, W, X, Y, Z, and so on. And then we will pass on to the different segments and then calculate the values of this one. This seems to be here, we are drawing the perpendicular bisectors of, we know that perpendicular to a chord, from a chord to a center bisects a chord. So we know that P and Q are the midpoints of the chords AB and CD respectively. So when we get the two parts, AP is equal to PB is equal to 4 centimeters, 4 units, because the entire length of the AB is 6 plus 2, 8, which is half of it is this one. So when you use coordinate geometry, it will be much easier. The second method is quite easier. We find the coordinates of the point P and Q. Then find the O, the OA and OB. We already take M as the origin and then proceed. A hint has been given here. We are going to cover this detailed solution in a separate video later. So stay tuned. And what did we see this in this video? We just saw something interesting about the concepts, advanced concepts means circumcenter, we went to the intersecting chords theorem, and circumcenter, the incenter, and the incircle and the circumcircle and the circumcenter. So these are the topics we covered in this video. Thanks for watching this video, and this is all you need to know, advanced concepts about circles. This concludes this part of the video. Thank you.